with a double degree. Not guilty. Giselle graduated from the double degree in physics and mathematics at the University of Strathclyde with first honor class degree, where she also obtained the Frank Leslie Prize for the best student graduated in the double degree. And then she moved to the doctoral training center, joined by the University of Edinburgh and the Heriot-Watt University, where she did the PhD in mathematics. After that, she moved to Paris, to the Sorbonne University, as a postdoctoral researcher in the group of Professor Benoit Partam, who is a former student of field medalist Pierre-Louis Lyon. And from there, then she moved again to the Basque Country, to the Basque Center for Applied Mathematics, joined with the University of Oxford. And in the meantime, she got a position as assistant professor at the Polytechnic University of Barcelona. And during this year, she's visiting fellow of the Institute of Mathematics in Oxford. So her main research area is, broadly speaking, mathematical biology, with many different interests touching different areas of mathematical biology, including a little bit of complex systems and networks. And her main topic or a specific topic of research is in differential equations, linear, nonlinear, and fractional differential equations. So today she's going to talk about diffusion and super diffusion in metaplexes. Thank you.
Thank you very much, Ernesto, for the introduction. So, and thank you very much for inviting me to give a talk here, even though I came in the worst days of weather, very cold and rainy, but I hope I come back when the weather is also good. So as you said, I'm going to talk about diffusion and super diffusion in metaplexes. And this is a joint work together with Ernesto Estrada and also with Heiko Gimperlein. So first, I'm going to start with some brief motivation of why are we interested in these systems, in studying these metaplexes, and also I'm going to introduce some main concepts that I'm going to use throughout the talk. Then I'm going to introduce you a metaplex, and then also diffusion and super diffusion in metaplexes. Towards the end, I'm going to discuss a toy model, where we are going to see some of the main characteristics and properties of the metaplex. And I'm going to conclude with two real-world examples of metaplexes. So I'm going to use a lot the term super diffusion. So I thought that it was good to give a brief introduction about super diffusion and how it's related to fractional diffusion operators, such as the fractional Laplacian, just to have everyone on the same page. So the diffusion process is described, as we all know, at the particle level by a Brownian motion, right? It's a random walk. And one of the main characteristics of this movement is that the mean square displacement grows linearly with respect to time, right? So then the distribution of the displacements in this case follows a Gaussian, and what we see is a very localized search, right? In this case, the case of diffusion is described at the macroscopic level by a Laplace operator. On the other hand, for the case of the super diffusion, it is described at the particle level by the so-called Levy motion. Okay, and in this case, the mean square displacement grows non-linearly with respect to time, and in particular, for values of alpha between 1 and 2, it grows faster than just linear, describing this type of non-local diffusion. Okay, for example, here we see a strong presence of long runs or long jumps in a space, which gives the non-locality of the movement here. Also, in this case, the distribution of the displacement follows the power law, okay, heavy tail distribution. And at the macroscopic level, this is described, at least in the continuum, by fractional Laplacian operators or fractional differential operators in space. But what is the connection between these non-local movement and the fractional Laplacian, the continuous fractional Laplacian. And this is a very formal explanation of the fractional Laplacian, but I find it very intuitive, especially for young people that haven't seen this type of operators. It's very intuitive to interpret it. So let's go back again to the diffusion case. So we have a typical random walk in a 1D lattice, and this particle can give a jump to the left with probability 1/2 or to the right with probability 1/2. Then at time t plus delta t, the probability of finding the particle at position x is given by this expression. This is very well known by everyone in the audience, right? Then what we do is we do some manipulations here, and we try to write this in terms of different quotients, right? So we add uxt on both sides, or we'll subtract uxt on both sides. We do some rearrangements here. And in the limit, when the x and the t goes to 0, what we obtain is the classical heat equation, right? So we start from a classical random walk, and we end up in the heat equation. Now, what happens if we allow this particle to give long jumps? The same idea, but now we give long jumps. Well, in this case, the probability is not 1/2 anymore, but it decreases algebraically with the distance of the jump. And if we do exactly the same analysis as before, we can write this expression here, where again, we don't have 1/2, but we have some other probability that depends on this distance. Now, if we continue, we can rewrite this probability here in some smart way, because we have to be careful with the scaling. But what we see is that in the limit of this expression, what we obtain is a fractional diffusion equation, where beta is equal to n plus alpha, where n is the dimension of the space. And this is the definition of this operator here in the continuum, at the continuum level. So we have this fractional Laplacian is defined in this way, where PV is the Cauchy principal value of this integral, and C alpha n is some normalization constant that depends on alpha and n. So here, what we have done is basically just taking the limit. This becomes the Riemann integral of some singular kernel. Okay, and this gives the non-locality of this operator. Okay, so now I'm integrating in the whole Rn with respect to this singular kernel. Okay, there are many different definitions of the fractional Laplacian at the continuum level, but this is the most classical one, and also you can find them written in terms of Fourier, which is also very handy when you have to do some computations. In recent years, there has been a lot of interest in superdiffusion processes connected to biological systems, but also connected to more analytic aspects of this operator. In particular, for the superdiffusion modeling, there has been some work done by Benoit Pertin and Ming Tan in cell movement, but also by Clément Mouron and Mellet in kinetic equations. Of course, there is also a huge literature on numerical methods to solve this type of operators, and also on analysis for this type of operators. During my PhD, I worked on the modeling using this fractional Laplacian, more focused on biological systems and also on interacting system of particles. One of the examples was robot, but you can think of any other interacting particle system. The thing here, the interesting thing is that in all these cases, we studied the process, this non-local movement in Rn, or in nice domain as a square table. We didn't include any complex geometry in this to describe this non-local behavior. So what happens if we want to study this non-local diffusion, this superdiffusion, in more complex domains, such as the brain, for example? Well, in this case, one of the typical assumptions is to approximate each of these brain regions by point nodes. And then we study the diffusion or superdiffusion across the network. Okay, but of course, with this approximation, we lose a lot of information about the things that are happening inside each brain region. And we don't know if what we observe at the macroscopic level is a result of this internal dynamics. So what we propose here, also, you can think about a very non-convex domain, such as this one, and study a superdiffusion process in here. So what we propose is the following. So we give some structure to these nodes. Okay, so we say that the nodes are not going to be points anymore, but a domain in R2. And then what we do is we consider a continuous diffusion process in each node, coupled with a discrete diffusion process across the network. Okay, and this network of subdomains is what we called metaplexes. Okay, so in the following, where I'm going to try to discuss, and please interrupt me at any time if you have any questions. What I'm going to describe is a normal diffusion process, well, or a superdiffusion process inside each node, which is going to be a continuous process, together with a discrete diffusion or superdiffusion process across the network. And of course, you can think about many other examples. So let's think about metapopulation dynamics, right? Where you have cities that are interconnected, but you have some processes happening inside each city and at the same time happening across the country, let's say. Also, another very classical example, and also we are going to discuss this as a real world metaplex later on, is for the case of foraging strategies of animals. So you can think about a landscape that is divided into patches, and then the animals do a search strategy inside of each of these patches, but at the same time they have to look for resources in other patches of land. Another classical example could be climate, the study of climate. So you can think about the atmosphere and you can divide it in different regions, okay? And then you have different processes happening inside each region. So you can think about Navier-Stokes or geostrophic equations inside each of these regions that at the same time are interconnected, okay? So that's the main idea of the metaplexes, to not lose the information inside the nodes, to use this information to see what happens at the macroscopic level. So the main question I'm going to try to answer here is how the global dynamics in a network is affected by the internal structure of the nodes. And in particular, I'm going to focus on these three things. So I'm going to focus on the internal dynamics, which in this case is going to be diffusion and superdiffusion. But again, you can think about any other dynamics that you are interested in. We are also going to look at the geometry. So how the geometry of the nodes affects the diffusion. You can think of small nodes or big nodes. It depends on your problem as well. And also how these nodes are connected, okay? If they are connected through the boundary. So for example, in the case of cells forming a tissue, you have that the cells are connected through the cell membrane, but you can have other examples where the connection between the nodes is not through the boundary, but through other points inside the node, okay? And how this affects the dynamic that you observe in the network. Okay, so here is the formal definition of a metaplex. So it's a four-tuple gamma where VE is a graph. So V is the set of vertices, E is the set of edges. Little omega, it's a set of different domains. So for each J, you can think of a different geometry. You can have, again, any geometry that you want in the nodes. And I, it's a map that assigns to each vertex a different geometry. So this is a very general definition of a metaplex, and also very complex to analyze and to show any results. So that for that reason, we are going to use a simplification, okay? So we are going to consider that all the nodes have the same geometry, so they are balls of radius r. They have embedded a Lebesgue measure so that we take into account densities. And of course, the map I is constant because all the nodes have the same geometry. Okay. And here we have an example of a linear metaplex, which I'm going to discuss in detail later, but just to give you an idea. So omega-1, omega-2, and omega-3 are the different nodes, which you see that are continuous domains that are coupled through points that I'm going to discuss in detail later. Okay, so this could be a typical example of a metaplex. Now, as I mentioned previously, we are going to describe a discrete diffusion process across the network and a continuous diffusion process inside each node. So I'm going to start with the discrete diffusion that is described by this equation here, okay, where U is the density of the diffusive particle or super diffusive particle. We start with some density U naught. Here, D max is the diameter of the network, and delta D is the D-path Laplacian operator in the graph, which is defined in this way, where D is the shortest path distance between two nodes. So you can think about this one, for example, for D equals to 1, this is the classical Laplacian operator in the graph, okay? But this one generalizes the classical Laplacian operator, because in this case, you are allowing the particle to jump not only to nearest neighbors of distance 1, but to neighbors that are at the distance D from the initial condition, okay? Yeah.
You also allow gaps for distance lower than D, or only for distance that are equal to D?
For distance that are only equals to D.
Only equals to D.
Yeah. Here, CD, it's a parameter that tunes the hopping of the particle between short range and long range. So the long range is given by the Mellin transform of this D-path Laplacian, and the short range hopping is given by the Laplace transform of the D-path Laplacian. In this case, you see that for the long range, the probability decays algebraically with the distance D, while in the case of the short range, this probability decays exponentially with the distance, okay? Here as net, it's a parameter that we are going to vary in the future numerical experiments. And for S net close to 0, we approach to the super diffusive case. For S net going to infinity, we have a normal diffusion process, okay? And this is the way of varying the dynamics in the network. Now we are going to discuss the continuous diffusion inside each of the nodes. So in this case, we have that the density Uj in each of these nodes Vj evolves according to this equation here. This is the fractional diffusion equation, where S node, again, is another parameter that we are going to vary for the numerical experiments that takes values between 0 and 1. So when S node is close to 0, you get super diffusion. When S node is close to 1, you get normal diffusion. And this fractional operator is defined exactly the same way that we saw before. So basically, it describes the super diffusion behavior at the continuum level. This problem is solved using some finite element methods that are quite complicated to explain, but we consider this process in bounded domains imposing Neumann boundary conditions, okay? So nothing escapes through the boundary in these cases, okay? So I think now we are in a good shape to describe the diffusion in the whole metaplex. So we start by defining U, which is a vector where each of these entries is the density in each of the nodes, and the diffusion in the whole metaplex is defined by this expression here, where D is an n by n block operator matrix, where n is the number of nodes. Here, the matrix H is diagonal matrix that describes the diffusion inside each of the nodes. So J is the flux, divergence of this flux give me the diffusion process in each of the nodes. While this capital T gives the hope of the diffusive particles across the whole network. And these Tij are the transition operators between two domains. And this transition operator is given in terms of sink and sources. So a sink, it's a subdomain inside of omega-1 that the diffusive particle will leave these domains through the sink and will appear in the source in the other domain with certain probability. Okay. Alpha ij are the transition probabilities, which basically describes the strength of the coupling between the nodes. So you can think of nodes that are weakly coupled or nodes that are strongly coupled. Yeah.
I don't know. So whether I hop from touch 1 to 2 depends on where in touch 1 I am. Well, I can.
Sorry,
So
if you.
In the domain omega-1, touch 1. Can I hop to 2 or the hopping rate to touch 2? Independent of where?
No. You can hop to patch 3 with certain probability, depending on how the nodes are coupled.
But not depending on where in node 1 I am. Where exactly in node 1 I am.
Well, you have to be closer to the sink to start hopping to the other nodes. But whether you hop to node 3 or 1 or 20 depends on how they are coupled. If you have long range coupling, then with certain probability you will hop to node 10. If you have short range coupling, you most likely not jump to node 20.
You have to be inside the domain of sink.
Yeah.
So the sink, they depend on where in node 1 I am.
Yeah, you can think about, you have a domain, right? And you have the solution of the heat equation. Let's think about it. So you have this discretized. So this is a mesh inside the domain. And you have the solution in all these nodes, right? And you define that your sink is going to be in this area, right? This is the sink to the other domain. So basically what you're going to do is you're going to transport this mass or this density to here with certain probability, okay? And the strength of this coupling is going to be given by alpha. In this case, we consider that the coupling is homogeneous, so all the nodes are coupled in the same way, but you can think of different couplings. For example, I was talking with Manuel the other day, so you can think, for example, that alpha depends on the degree of the node, right? So if you have a node with high degree, then the coupling is stronger, or if you have a node with low degree, then it's weaker. Depends on depends on the process that you want to describe. But for this talk, alpha, it's homogeneous in the whole metaplex. So now we are going to start with the toy model, okay? And the toy model is a linear metaplex of 51 nodes that are formed in they are coupled in a form of a path graph. So they are all in a linear way. As I mentioned, and I'm going to start the process with a uniform distribution in node 1, okay? And what I'm going to do is I'm going to see how this uniform distribution diffuses across the metaplex, okay? As I mentioned previously, we are going to vary S-net, which controls the diffusion in the network, and also S-node, which controls the diffusion inside the node. I'm going to consider different sizes of the nodes, so small nodes of radius 1 or big nodes of radius 100. We are also going to consider different coupling points. So either all the nodes are coupled through the center, or they have disjoint sink and sources, as this example here. Okay, so they are disjoint, or they can be coupled through the center. And finally, of course, we are going to consider different nature of the coupling. So either they can be short-ranged or long-ranged. Okay. So first, I'm going to give you some spoilers of the results. And then I'm going to give you the actual experiments. So some spoilers that I can do right now are the following. So for example, we are going to see in the experimental results that the internal superdiffusion accelerates the hopping in the whole metaplex, but the equilibration of the density is slower. This is totally counterintuitive, and I'm going to explain why, but I'm going to give you this piece of information without giving you the answer, okay? So this is not what you expect, but it has a reasonable explanation. Then we are going to see that the geometry and the coupling points of the nodes play a crucial role in global dynamics. This is not a surprise, okay? This is something that you might expect. Also, we are going to see that the superdiffusion inside the nodes accelerates the diffusion in the metaplex, but it doesn't change the nature of the diffusive process in the metaplex. So whatever the internal dynamics you have in the nodes, it's not going to change the dynamics of the metaplex. If you have superdiffusion in the metaplex, or if you have normal diffusion in the metaplex and you put superdiffusion inside the nodes, you have faster diffusion, but not superdiffusion. Okay?
Just in this time, not in general.
Yeah, no, yeah, this is, yeah. And also, finally, for the small world metaplexes, which also I'm going to introduce later, the external dynamics doesn't play any significant role in the diffusion, well, in the dynamics of the metaplex. So small world metaplexes are densely connected networks, and we are going to see that in these cases, the dynamics is completely dominated by what happens inside the nodes. And this is also very interesting for many application purposes. And we are going to discuss this with the real world metaplex. So let's go to the numerical experiments. So here what we are going to analyze is the influence of the internal dynamics. For this, we consider nodes that are coupled through the center and that the coupling range is short. And what we are going to see is the evolution of the density inside each node. So here we have the density, and here we have the different nodes from 0 to 51. And we look at this at different times. So t equals to 10, 100, and 1000. So as we see at the beginning, so for shorter times, superdiffusion inside the nodes, which are the red, forget about the crosses and the circles. Let's only focus on the internal dynamics. So the red is superdiffusion inside the nodes. And we see that in both cases, superdiffusion inside the nodes accelerates the diffusive particles, right? So the superdiffusive particles can travel the whole metaplex faster. But for longer times, we see that the blue one here, which is normal diffusion inside the nodes, equilibrates the density faster than normal diffusion. And as I said previously, this is very counterintuitive, but you can think that you have, this is due to the nature of the superdiffusive process. So again, you have a domain, and in this case, you have the sink and the source in the middle, okay? And you have a superdiffusive particle that arrives here, and very quickly, it jumps far away from the sink. And then it takes some time for the particle to find the sink and move to the other node. However, for the normal diffusive particle, even though it's slower, it's more effective, because when it arrives here, it might stay around for some time and find the sink faster. So the super diffusive particle travels the metaplex faster, but the normal diffusive particle is more effective in equilibrating the density. Now we look at the influence of the node size. Okay, in this case, we consider disjoint sink and sources, and again, the short range coupling. And what we look at here is the equilibration of the density in node 1. So remember that U naught is the initial density, and N is the total number of nodes. So this should converge to 0 as time passes. And what we have here is this equilibration of the density for different times for the case of small nodes and big nodes. So let's forget about all these values here because they are very complicated and small. The continuous line are super diffusion inside the nodes, and the discontinuous line are normal diffusion inside the nodes. Again, what we see is that for the case of its small nodes, the normal diffusion inside the nodes equilibrates the density faster. While for the big nodes, the opposite happens. So for the big nodes, the super diffusion inside the nodes equilibrates the density much faster than normal diffusion. And again, this is because of the same reason, because for the case of the big nodes, what we have, it's very localized sink and sources. So we have a sink and a source. So the super diffusive particle has advantage over the normal diffusive particle because it arrives here, and due to the nature of the process, it can jump very far away very quickly and find this one faster. While if you are in a small node, then you will have the same problem as I explained before for the super diffusive particle. So, of course, then the geometry of the nodes plays here a crucial role on whether the super diffusive or the diffusive is more effective in equilibrating the density. This can also be seen analytically by looking at the spectral gap of the operator capital D. Remember that this operator was H plus T. And as in networks, this equilibration time is the inverse of the spectral gap. And here what we do is we plot the 10 first eigenvalues of this operator for different values of epsilon, for different strengths of the coupling, okay? By strength of the coupling, I mean by different strengths here, okay? So what we have then is eigenvalues for different strengths of the coupling, and on the left we have the results for the small node, and on the right for the results for the big node. And again, the crosses are the super diffusion inside the nodes, and the circles are normal diffusion inside the nodes. For the case of the small node with super diffusion inside the nodes, the spectral gap is smaller, which means that the equilibration time is bigger. And the opposite happens for the case of the big node, where super diffusion inside the nodes have bigger spectral gap and therefore smaller equilibration time, which validates just the numerical results that we saw a minute ago. Okay. Then the last test for this metaplex, for this linear metaplex that we are going to discuss, is whether the internal dynamics can change the nature of the diffusion process in the network. And by nature of the diffusion process, I mean whether super diffusion can lead super diffusion in the network. Okay. On the top, we have short range coupling. And again, we have the density in the nodes. And here we have the nodes at different times for t equals 10, 100, and 1000. And notice that here we have log-log plots. And what we observe is that independently of what is happening inside the nodes, so it doesn't matter if it's super diffusion or normal diffusion, the density decays exponentially, which means that it's a diffusion process, which means that it doesn't matter what I put inside the nodes. If I have short range coupling, then diffusion inside the nodes is not going to change that. Okay, so super diffusion inside the nodes is not going to lead super diffusion in the network if I have short range coupling. And the same happens if I consider the long range coupling. So here we have, again, the density and the number of nodes. And now these colors are different times. And here we have for SNet equals to 1.5, 2, and 2.5. And for the long range coupling, again, it doesn't matter what I put inside the nodes, I always get a linear decay of the density. So I always get super diffusion. So again, the conclusion is that super diffusion inside the nodes accelerates the hopping, but it doesn't change the nature of the process. So any questions so far before I go to the... Yeah, it's independent. It only depends on the range of the coupling. You have short range of the big network, yes. Yeah, absolutely.
But eventually, that sort of coupling, steam can destroy in the same ways. And you consider that this lighting distribution is something wrong with the rays. The rays are coupling. And by eventually get
into a diffusive one.
Yeah, something which is faster. If you can think that you have a connection, I'm thinking that you have a connection, but each of them the nodes are connected to the same time. You have super diffusion. Now we already kind of connection within them.
But you mean you delayed? You don't do it artificially, just by the. But we didn't observe any change in there. So if you do these same plots, exactly the same plots using the connection through the middle, it doesn't change. Yeah, it's long range then.
The second one is long range and this diffusive one.
Yeah, you have here diffusive, super diffusive inside the node and diffusive inside the node. We did also the test with the internal couple. The crosses are normal diffusion, so they almost overlap. You see that the crosses and the circles are super diffusive inside the node, and they all decay algebraically. They don't change that much, especially at longer times. Especially at shorter times. Yeah, there's not a big difference because the process is too fast. In general, if you have long-range coupling, the process is too fast. For example, for short-range coupling, what you have is very similar to what I described before. At the beginning, super diffusion is winning inside the node. So it's this one here, it's node 0.2. But at long times, you see that normal diffusion starts to win and then equilibrates faster at the end. So it's independently of the coupling points. If the node is very big, then what you have is the opposite. what you have is exactly as in here. So you have that for the small node, normal diffusion wins equilibration, and for big nodes, super diffusion wins equilibration, just as in here, this explanation. It's independent of the coupling points. It's just given by the nature of the process inside the node and by the nature of the coupling. So here you have short range and long range. So normal diffusion in the network and super diffusion in the network, and you have both processes inside the node. So super diffusion and normal diffusion, and here the same, normal diffusion and super diffusion. And you observe the same. Any other questions or comments? Okay, so the last two examples are real-world metaplexes. So the first one is the fragmented landscape in Madagascar that is fragmented in 183 patches, which corresponds to the nodes of the network. And in this case, we are going to see that this landscape metaplex is very similar to the linear metaplex that I just described, to this toy model of 51 nodes. Here, the diameter of the metaplex is 32. The average degree of the patches is 5.78. So somehow it's similar to the linear metaplex, and we are going to see this also in the numerical results. The second example is completely different. It's a metaplex of the macaque visual cortex, where this visual cortex is divided in 30 regions, which are the nodes of the metaplex. And this is an example of a small world metaplex. And this means that it's a very dense connected network. I think we computed the density and it was 0.44. So it's very densely connected. Here, the diameter is only 3. And the average degree of the nodes is 12.67. Okay, so we have two very different metaplexes, and let's see what happens when we do the same test. So we are going to vary the diffusion inside the nodes, and we are going to see what we get at the network level. So we start with the landscape, but of course here we have a question. So where do we start the process? Of course, previously, we started the process in node 1, but of course now we have highly connected and lower connected nodes. So where do we start the process, and what difference does that make? And what we do was a simple test. So we started randomly in some lower connected nodes and also in some higher connected nodes, and we computed the distance. So here we have the average density with respect to the distance to this initial condition. Okay, and we see that in both cases, so whether you start in a lower connected or in a highly connected node, there is no difference in the decay of the density. So there is no difference on whether you start your process in a highly or lower connected node. Okay, for the purpose of this test. So then what we did was to start in a node randomly. And what we observed was very similar behavior to the linear metaplex, which again was not surprising. So here at the top, we have the results for the big nodes. And at the bottom, we have some results. These are for the small nodes, and these are for the big nodes. And for example, if we focus on this figure here, the black line is normal diffusion inside the node, and the green one is super diffusion. And we observe the same counterintuitive result, right? So for normal diffusion inside the nodes, the density equilibrates faster than with super diffusion inside the nodes. And the opposite happens for the case of the big nodes, also in this landscape metaplex. Okay, so in this case, we have the green, it's again the super diffusion. And we see that for the case of the big nodes, super diffusion equilibrates the density faster inside the node. So it's exactly the same result that we obtained for the linear metaplex. However, when we look at the macaque visual cortex metaplex, what we observe is totally unexpected. So for this case, the internal dynamics completely dominates what happens at the metaplex level. So in this plot here, we have very different dynamics in the network. So SNet is 0.4, so very super diffusive. And the red one is 4, so very diffusive. And the density equilibrates almost in the same way, which means that here the power is all in what happens inside the nodes. Okay, the dynamics of the nodes controls the dynamics of the metaplex, independently of what you put in the network. So I'm going to remind you again of the results just to start wrapping up. So we saw that the internal superdiffusion can accelerate the hopping across the metaplex, but the global equilibration is slower. And remember again this picture here, okay? Also, we saw that the geometry and the coupling points are very important and play a crucial role on whether you have faster or slower equilibration. Also, we saw that superdiffusion inside the nodes accelerates the hopping, but it doesn't change the nature of the diffusive process in the network. And finally, we saw that for the small world metaplexes, something very unexpected happened. And in this case, the dynamics of the metaplex is completely controlled by the diffusion process happening inside the nodes. It's completely controlled by the dynamics that you put inside the nodes. Okay, so just some very general perspectives of this work. So far, I've been talking about diffusion and superdiffusion processes, but of course, you can think of any other dynamical process that you want. For example, you can put synchronization or any other type of dynamics. You can also consider subdiffusion, either inside the nodes or across the metaplex. And you can also think about concrete applications of these metaplexes, for example, in the case of swarm robotics. So if you have to search a certain area that have rooms and corridors, you would like to obtain the most efficient parameters to have an optimal search strategy. And metaplexes, of course, is a way of describing this search with obstacles and rooms and corridors. And with that, I think I'm going to conclude. Thank you very much for your attention.
So thank you very much, Giselle, for the talk. I want to call your attention what you were saying at the end. So I could call the brain network maybe super small world. Is really very, very dense in comparison with most of the small world networks. But the results point out that the network plays no role there. So what really it is a continuum space. So playing with the network there, possibly not a good idea from the type of information that you can obtain. So this is a thought-provoking comment. Of course, most of the real-world networks are not as dense and as super small world as this one. So typically you have logarithm, so that the average path length scale of the logarithm of the number of nodes. Here you have much smaller than that. But anyway, so you have questions or comments now. Any question? Don't be afraid. Yes, please.
If I understand well, you model the nodes as a continuous medium.
Mm-hmm.
And how do you send particles from one node to the other? I mean, you have this continuous density function, I suppose.
Mm-hmm.
And with some probability, you...
Yeah, it's like when you have a node, okay, what you do to have a continuous solution at the end is discretize in a mesh, right? So because you solve, imagine you solve a heat equation in a bounded domain, and at the end what you have is a solution in a discretized domain, okay? So basically you have the solution at these points, And what you do is you define your sink. And you say that this density here, or these solution points, are going to be mapped to the next node with certain probability, or to the other one with certain probability.
So you rewrite what is in the lower node with what you have there, no?
You basically imagine that you copy and paste this with certain probability, and then you let it evolve here. So inside the node, you always satisfy some type of equation, fractional diffusion equation. So when you put this density here, then this density evolves again according to this probability, and that will give you, well, another discretized solution. And then, I mean, you repeat the process. So you have the density at some mesh points, and you do the same. You define your sink, and you take this, you copy and paste it to the other one with certain probability, depending on the coupling.
And what happened with the density that you have previously and in the second node? I mean, you have continuity of the.
Yeah. I mean, the density is conserved across the metaplex.
You delete what you have in one node and you paste it in the next node.
Yeah.
You add it to the previous density.
No. You take this, you put it here, and then you let it evolve. Imagine that you start with some density, okay? So you start with a density distribution, okay? So this is your initial density. That is a Gaussian, right? But what does this really means is that, again, you have a mesh inside your node. And then you're going to have some values here, probably not so many values here because it's a Gaussian, and some values here, okay? And now you are defining this as your sink. So you're going to take these values and you're going to map them here. And these values here are going to evolve according to this equation. And at some point you will have some density here because it's a diffusive process. So it tends to diffuse. And then these values here are mapped to the next one, and so on and so forth. But this, let's say that this mapping here is instantaneous. You don't lose any time from here to here. It's instantaneous. It's like cutting and pasting with some probability.
It's like every time that you apply to the subdomain of the sink, you do, like in quantum mechanics, annihilation and creation. Yeah. So you annihilate this density and appears instantaneously in the other region, which is what you do in network theory in the diffusion equation. So, yep.
My question is, if the couplings were bidirectional, so you can go back, then what would change in this model? Because as I understand, the coupling is always one dimension. You always talk about sinks and sources, so you can never go back.
Yeah, I mean, it doesn't have a direction. The coupling doesn't have a direction.
Well, I mean, if there's a sink and a source, that there is a direction. A source is a source and a sink is a sink.
But yeah.
But that's another way. But within the same place, you cannot go back. You can put another connection. I agree, from the third layer to the first one.
No.
But within the same layer that now is a source. Say the second domain. There is a source on the left, which is a sink on the first domain. Can a particle go back?
Yes, this is two directional for sure.
So how do you implement that? Because this is not a copying from here to there.
Well, then the same happens from, I mean, this same diffusion, I mean, this same density that you have here can appear here and then go back. That's why you have an equilibration at the end.
But then how you define the dynamics of the sink? Which is the precise copying process that you
just taking this and putting in here, and the same happens. I mean, when.
But then how you bring a particle from 2 to 1?
But then when you have the density here,
yes.
it starts to diffuse immediately.
Okay.
And then in the next time step, the density that you have here is not the same as in the previous time step.
And then you copy that to the first one.
Yeah. Yeah.
And why not the one to the second one? I mean, it's.
No, I mean, at every time step, something different happens. So let's say the first time step, you take this and you put it here. This second time step, this starts to evolve.
Yes.
Okay. And then the density that you have here is different from the neutral
Yes.
one. But it has certain probability it can go back to here. That's why the superdiffusive process doesn't equilibrate, because the superdiffusive density goes back and forth. And that's why it takes so much time to equilibrate.
Not very clear.
It is
How you
possible that
implement
in the evolution, by some strange probability, it arrives to here and go back to here. So it will go back to here and
You
never.
know, that I understand. What I don't understand is how you put that on the differential equation.
On the different.
I mean, the values that you have at that point at a given time, and now you have the two domains. You have a time t. Now you decide whether you copy these values of domain A into domain B, or you copy these values of domain B into domain A, and let's imagine that you do that with a probability. There will be a chance that you get that the probability tells you to copy from A to B and also from B to A.
It's the same, you
And,
mean?
and that's allowed. Okay. Yeah, no, yes, so you can interchange the value
Yeah. There are,
Okay.
yeah.
in case.
Thank you for the talk.
Thank you.
I was wondering, because you showed us that there was an example, which was the landscape, where the structure of the network determined the dynamics, right? And then the Mackay, where it didn't matter at all. So I was wondering if there will be like a single network parameter that could determine if a network will be. Do you understand what I mean?
Yeah,
Like,
it's a very interesting question. For that, I think we need to do more examples. We need to do more and more experiments with networks that are resemble like the landscape, and other networks that are close to the macaque, and see whether there is some correlation in terms of the density of the network, for example. But yeah, it's a good question, but we need to do more experiments.
okay, thank you.
So if I understand this correctly, you don't really care so much where exactly inside a patch you are, only that you're in a region where you can exit, right?
Yes.
So you can generate, in principle, what you're asking is if a particle comes from the top to the middle patch, it arrives there at time 0, then you want to know at a later time, is it in the region where you can exit to patch 3 or not, right? That's all you care about.
Yeah,
right?
yeah. That's
so in principle, you could specify that as a function. A particle arrives at time t, and you say at a later time t plus t prime, what's the probability that it is in this exit?
Yeah.
Right?
Actually,
So then you don't need the internal dynamics in some sense, right? You could generalize the model in that way, or vice versa. For any given internal dynamics, maybe you can compute.
yeah, I mean, you can arbitrarily say what is the exit time. That's for sure.
But
That's what you mean.
The probability that you can exit. So
Yeah, you can arbitrarily define that without having any structure here. Is that what you're saying?
yeah, so you could so this model is a special case of that, right? You can invent a kind of general function.
In the case of the circles or the spheres, balls like here, maybe you can put a delay time there. Suppose that you have an irregular line kind of structure, you need the internal dynamic, because it will take very weird different times in one node and the other node.
Also,
all the nodes are different.
Also, the advantage of the internal dynamics is that if you have something real happening, you can control it. You know what is happening inside. Also, for these cases, also we characterize this time. So let's call it tau, which is the time that it takes for a particle to go here to here. But we did this only because we knew what was happening inside the node. Otherwise, this is arbitrary. You have to guess it or you have to impose it. Yeah.
Okay, before letting opening the sink and letting the particle go down or up, you wait for a time, like for the diffusion to happen in the nodes.
You wait the time step. Yes.
Okay, so a time step is the
time step is very small.
Okay,
Almost continuous.
so it's not really thermalized in some sense.
It's not?
Thermalized in some sense, the diffusion. I mean, inside the nodes, you wait for a time and then you open the sink, or okay.
Yeah.
And this time is correlated to the process inside the nodes.
Yes, of course.
Okay.
Yeah.
And have you tried to, I don't know, modify the time? And
no, we didn't. I mean, the time it's just a time step to wait for the solution of the heat equation or superdiffusive equation to be computed again.
Okay.
You know what I mean? But it's not related to it's only numerically. It's only related to the solution of the continuous process inside the node.
Okay.
But it's not related to the actual diffusion dynamics. It's just a numerical thing to compute the solution of the heat equation again and let it evolve.
Okay. Okay. Thanks.
Okay, so I think Giselle will stay here for at least 1 hour more. So you have any more question, you can knock in our door. So in the 1 or 2, so she will be there. Coffee is free if you bring it. So thank you very much for your attention, and thank you, Giselle, for the nice talk.